Good day, grade 11s. Today we are going to go through a physical science paper at Johannesburg-based district, and it's a June examination 2025. So it's chemistry paper 2. So without much further ado, let's proceed. The first page there we're having our instructions. Then first question 1 is multiple choice questions, and it reads: the bond energy of a Cl carbon and Cl there, C and Cl bond is 338 kilojoules per mole, whereas the bond energy of a Cl bond is 238. So the first one there is 338 kilojoules per mole for Cl. Then difference in the bond energy exists because the first option reads the bond length of Cl bond is greater than that of Cl bond Ci bond, which is carbon and iodine. This is incorrect. Then they're saying the chlorine is more electronegative than the iodine. This is also incorrect there. Then C reads the bond length of C to iodine bond is greater than that the bond of the Cl bond. Yes, we agreed with this, right? And then the last one was saying the chlorine atom is bigger than the iodine atom. This is incorrect. So according to this, our correct answer should be option C, which reads the bond length of Ci bond is greater than that of Cl bond. Okay. Then 1.2 reads the intermolecular forces in methane gas CH4 so we're looking at the intermolecular forces. The most important part there says the intermolecular forces that are found within our methane gas are. Okay, so now we need to know what type of forces that are actually found within an intermolecular gas. So it says the first option there, ion-induced dipole forces. This is not an ion-induced dipole force. And then B rays are London forces, okay, which are more of like weak forces that are actually found in CH4 there, right? Okay, these are forces that are found within the methane gas. I agree with option B, which are the forces, intermolecular forces that are found in methane gas, which is CO4. Then ion dipole forces, this is incorrect, as well as option C, and then option D, also hydrogen bonds. Remember, hydrogen bonds, your hydrogen should either be bonded to this fluorine, oxygen, or nitrogen for it to formulate hydrogen bonds. Then 1.3 reads bond length is the average distance between A, it says orbitals of two bonded atoms, bond length, okay. B says electrons in two bonded atoms, this is way out. Then orbitals of two bonded this is also, they are talking about orbitals here they're talking about electrons in the two bonded atoms, which is incorrect also. Then option C says nuclei of two bonded atoms, right? Then D says molecules of the same substance. This is incorrect. So our correct option there is going to be our option C, which refers to the two nuclei of bonded atoms. So we're talking about the average distance of the bond length. So it means here, if you're having these two atoms bonding together, what we are focusing on is the distance between the nucleus of each. So this nucleus versus the nucleus of the other one there. So they like that. So this is the bond length that we are referring to, the distance between these two. So nuclei there. So our correct option there is going to be option C, which says two is the distance between nuclei of two bonded atoms, like that. Okay. So then we proceed to question 1.4. which reads hydrogen bonds and London forces. Induced dipole forces have a common characteristic in that they are both intermolecular forces. They are actually intermolecular forces. Okay, so let's go through option 1. They're saying stronger than chemical bonds. They are stronger than chemical bonds. This is incorrect. Then both occur between non-polar molecules, also incorrect. And then they're saying here, option C, both occur between polar molecules, which is also incorrect. Then our option D says are both intermolecular forces. Yes, that's our correct answer there. They are actually both intermolecular forces there. Then we proceed to question Okay, so it means we are done with the multiple choice question part there. Then we proceed to question 2 that reads molecules such as carbon dioxide. Okay, so we've been given molecules such as carbon dioxide there, then and H2O are formed through covalent bonding, right? So the first thing that we are supposed there to define is define the term covalent bonding, right? Okay, so covalent bonding, it is defined as the sharing of electrons. So this involves the sharing of electrons, the sharing of electrons between between atoms to form a molecule, between atoms to form a molecule. Like that. That's how we define the term covalent bond. Then 2.2 says write down the number of lone pairs in the water molecule. Okay, so if we are to bond this H2O there, we'll take note of, like, let's say we're having my oxygen there, right? So my oxygen, if we're to check our periodic table at the bottom there, you will find out that oxygen is in period oxygen is in period number 6 there, right? So it means it has got a valence of what? 6 electrons. So 6 electrons on the outer shell, whilst our hydrogen there is in group 1, which means it has got, just 1 there. So if we can proceed and go up there, we'll show it how these actually bond together, oxygen and our hydrogen there. Okay, so we're saying if this was my oxygen there, right? So it means now let me just like draw, represent it using a smaller circle. So it means if I was to draw a Lewis dot diagram or Lewis structure for oxygen there, I was going to represent it like this. So it means here oxygen is going to have how many electrons on the outer shell? A total of 6. Remember, we start with 1 before we start pairing. So we're having a total of 4 there. Then if I'm to add another one there is now 5, then another one there, 6, right? Then our hydrogen on the other end, if I'm to draw my hydrogen here, since it's H2O, it means here we should be having, hydrogens, 2 hydrogens. Then if it's to draw again, come with these lone pairs there. There is going to be this other one and then this other one. So that's the structure there. Then here the question says, write down the number of lone pairs in water molecule, right? So the number of lone pairs within these water molecules are going to be a total of what? This first one, right? So this first one here are referred to as the bonding pairs. Let's just label them, right? So these are referred to as the bonding pairs. These are actually like involved in what? In bonding. And then these ones at the top there, those are which are already paired there, they are referred to as what? Lone pairs. Okay, so those are lone pairs. So in this case here, it says write down the number of lone pairs in a water molecule. So it means we're having the first one there at the top and also the second one at the bottom. So the correct answer there should be 2 there. Then we proceed to the next question, which is question 2.3, which reads draw a Lewis dot diagram for the following molecules, right? So they started with H2O. Already I drew H2O at the top there. If you can see, this is my H2O there at the top there. Okay, I can actually like draw it the other way around, but this is my Lewis dot diagram for H2O there. Then after that, we're also supposed to draw a Lewis dot diagram for the following, which is our HCN. So for our HCN, they were also going to say hydrogen has got how many electrons on the outer shell? Just 1. Then carbon is in group number 4, so it's carbon chiral. So it means it has got a total number of how many electrons? 4 electrons. Then we also have our nitrogen there. So if you can refer to nitrogen, nitrogen must be having how many? A total of 5 on the outer shell. Okay, so we're looking at nitrogen there. As you can see, it's in carbon number group number 5. Then carbon is group number 4. So it means this one has got 5. And then this one has got, for carbon has got 4, then nitrogen has got 5, right? So if we are to go back there to draw the Lewis dot diagram for nitrogen, starting with the nitrogen there, we'll find out that it has got 5 electrons on the outer shell, right? So I'm going to indicate them here: 1, 2, 3, 4, 5. So in this case here, if we were to refer to the lone pairs, it means our nitrogen has got only one lone pair. So if we were to draw this, we are going to label it like this, right? The Lewis dot diagram. I'll put an X for hydrogen there, then a dot for carbon there. It means carbon there. Then after that, the three of these, we're going to like push them to the central part so that they can actually formulate what you refer to as a triple bond between nitrogen and carbon then. Then after that, you're going to have an N there, then with the lone pair on this other end. So this is how we represent our Lewis dot diagram for HCN there. Then actually we proceed to the next question, which says 2.4, question 2.4 reads, H3O plus ion is formed when H2O molecule forms a bond with an H ion plus, okay, with an H plus ion. So H3O plus ion is formed when H2O molecules forms a bond with an H plus ion. Then what type of bond is formed between H2O and H plus there? So we need the name of the bond, right? So if you can look at this, this is already an ion. As you can see, is H3O plus there is an ion, right? Okay. Then is formed when H2O molecules forms a bond with the H plus ion. So if you can see, the H plus ion there doesn't bring anything. So ion is formed after this H3O plus is formed after H2O is bonded to what? To this H plus ion there. So as you can see, this H plus ion is not bringing any electrons. Therefore, if there is one of these that does not bring electrons, so it means now we're going to have what you refer to as a dative covalent bond. So what type of a bond there? It is referred to as a dative covalent bond. Dative covalent bond, right? Okay. Sometimes they refer to it as a coordinate bond. Then 2.4.2 says they draw the Lewis diagram for the H3O plus. Okay, so for the H3O plus now, what we are supposed to indicate is to show where the H plus is going to like to be, right? Okay, so now let me just like make use of this space here. So I'm going to start with the H2O molecule, right? So if I'm to draw the H2O molecule, what I'm actually going to have is since I'm already having H3O plus, I'm going to start with my oxygen there. Okay, so we know oxygen has got how many on the outer shell? A total of 6 there, right? Okay, so I'm going to say 1, 2, 3, 4, 5, and then let me add the one at the bottom there, 6 like that. Okay, so then now we're also having the hydrogen that is being attached to this oxygen, right? So this other hydrogen is going to be here, and then this other hydrogen is going to be on this other end like that. Okay, so now we're having something like that, but then now because now we're having this other hydrogen, this H plus ion there, that does not bring anything on the table, so we're supposed to put it either at the top or at the bottom, but I'm going to put it at the top there. Let me use a different color. Let me put it in red so that you can see it at the top there. So that's your H plus there. After that, you're going to represent this one using like a square bracket, then like that, and then put a positive on the outer end, so to show that this is a type of what a covalent dative bond or a coordinate bond. Then 2.4.3 says state 2 conditions for the formation of a type of a bond mentioned in 2.4.1, right? Okay, so here a condition, the first condition is that the atom, one atom must have a lone pair of electrons. So one atom must have a lone pair of electrons. I'll just like write E negative there. That's the first one, right? So as you can see here, our oxygen was already having how many lone pairs? 2 lone pairs there, right? Okay, so it must have a lone pair. It must have a lone pair of what? Of electrons. Then the second one there, is that one atom must have an empty valence orbital. Okay, one atom must have must have an empty valence orbital, an empty valence orbital. Okay, orbital. Okay, so here by this we are referring to the outer shell. The outer shell should be empty. For example, if we're having hydrogen, in this case here, it was hydrogen when it was neutral, but after now it lost this electron. So it means now it has got what? Zero electrons. So if it has got zero electrons, it's just n what? An H there. So it means now if we were to throw it, there wasn't gonna be anything around hydrogen there in terms of electrons because it already gave out its what is electrons. So that's why we're saying one atom must have an empty valence orbital. The outer shell must be empty. Then we proceed to question 2.5, which reads, the polarity of molecules depends on the difference in electronegativity and the molecular shape. Okay, so here we're talking about the electronegativity depends on electronegativity and the molecular shape. Then after that, we've been asked to define the term electronegativity. Okay, so by definition, electronegativity is the tendency of an atom in a molecule to attract a bonding pair of electrons towards itself, right? So I'm going to write it down here. It says the tendency, let me change to blue, the tendency of an atom in a molecule to attract bonding electrons closer to itself or towards itself, like that. Okay, so that's how we define electronegativity, the tendency of an atom in a molecule to attract bonding electrons towards itself. Then we proceed to question 2.5.2 there, which reads, explain the difference in polarity between carbon dioxide and H2O by referring to the polarity of the bonds and the shape of the molecules there. Okay, so now we need to differentiate the polarity. We need to differentiate the polarity between carbon dioxide and H2O by referring to the polarity of the bonds and the shape of the molecule. So polarity of the bonds and the shape of the molecules, right? So in this case, we're going to talk about the bonds first, right? We're going to say both molecules are polar. Both molecules have polar bonds. Okay, that's the first point of call there. Then after that, and then this is due to their differences in electronegativities. Okay, this is due to their differences in electronegativity. Okay. Then after that, now what are we referring to? We're referring to the carbon and oxygen, and as well as what hydrogen and oxygen. So this is due to their differences in electronegativity. Let me be specific. We can say between carbon and oxygen, or hydrogen and oxygen, as well as carbon and oxygen, like that. Okay, then now we proceed to refer to the shape, right? Okay, Shape for water, shape for water, shape for water, shape for water is angular, angular like that, okay? And therefore, this makes this molecule to be polar. This makes water to be a polar molecule. Molecule, right? Okay. So why do we say this R is actually like make it polar? It is because one of the side of the molecule can be positive and the other is going to be what? To be negative. Okay, just in bracket. Okay, one side can be can just say slightly positive, positive, and the other be slightly, let me just say negative like that, slightly negative. Okay, that's what we're having. Then in terms of the shape for carbon dioxide, okay, carbon dioxide molecule, CO2 yes, a linear shape. Linear shape. Carbon dioxide has got a linear shape, and then thus it is non-polar. So we're going to formulate a non-polar molecule. And then the reason behind is because of the distribution of the charge, right? Okay. So charge distribution here, charge distribution is symmetrical. Is symmetrical. Should be an S there. Is symmetrical. Symmetrical. Okay, it's an S there. Symmetrical like that. Okay, so now we're done with question 2.2. Then we proceed to the next question. Question 3 there is the graph below shows the relationship between potential energy and internuclear distance between two hydrogen atoms, right? Okay, so now what we know here according to this at C there, these atoms we can see we're having this H and then this other H there. They are actually what a distance apart. They are at first there they are distance apart. Then this is my other hydrogen there. There is a space apart, right? Then what happens here at B there is that they approach each other. Okay, so it means here now they are like that, right? Then after that, at A, then they are too close to comfort. Then that's why we're having A with increased out in potential energy there, because now these two are now too close for comfort after B, they're going to A. Then the first question asks us to define the term bond energy, right? Okay. So bond energy is defined as the energy needed to break 1 mole of a compounds molecules, okay, compounds molecules into separate atoms, separate atoms. That's what we refer to as bond energy. Energy needed to break 1 mole of a compound's molecules into separate atoms. Okay, then we proceed to question 3.1.2, which says which point A, B, or C on the graph represents the point of maximum force of attraction between the nuclei of the two hydrogen atoms, right? So there we are going to have our answer is point B there, right? So that's what I actually showed there. So our correct answer is going to what? To be B there. So answer is B, maximum force of what? Of attraction, right? So as it goes up there at A, they are now too close for comfort, and then now there is repulsion. Remember, the nucleus of an atom is actually what, positive, and the other one is going to what, to be positive. So if they are too close, these two, they are going to what, to repel each other like that. Okay, then we proceed to answer question 3.2 that says consider the following table. Then we're having a bond there, which is carbon to carbon single bond, then double bond. We're having a triple bond again. Then that's the bond NH there. Can you see as you go down there, as you're increasing the number of bonds there, or bond order, our bond energy also what, increases there. Then it says which one of the bonds shown in the table above will have the shortest bond length. Okay, so there what you're going to have there is a C triple bond, right? C triple bond, right? So according to this, the higher the bond order, the higher the what, the bond energy. Therefore, it means now the bond length is going to be what, to be shorter there. So the one that shows above that is going to have the shortest bond length is going to be what, the last one there, which is C triple bond what, C, because there is a greater energy in terms of what, the bond energy there. So these actually are closely attached. Bond strength becomes what, high. Then give a reason for your answer to question 3.2.1, right? Okay, so we're going to say the higher the bond order, the higher the bond order, the higher the bond order, the bond order, the higher the bond order, uh the stronger the force of attraction, right? The stronger the force of attraction, like that. So if we are increasing our bond order, it means now the force of attraction becomes what, stronger. So what does that mean? So it means here the nuclei comes closer, relating in what, in a shorter length. The nuclei I come, okay, come closer, resulting in a shorter length, in a shorter length. Okay, that's how we're supposed to attempt question 3.2.2. Then we proceed to question number 4. Question number 4 reads in the table below, the boiling points of 4 hydrogen halides are given. In the table below, the boiling points of 4 hydrogen halides are given. So we are given from A to D. Then differences in boiling points there, can you see? So it means now they're decreasing from left going to the right there. Okay, so the one with the lowest there is going to be point at D. Then the one with the highest there is going to be what, HF, with the temperature boiling point of 19.4. Then the first questions ask us to define the term boiling point, right? So boiling point is defined as the temperature. So this is the most important part. So you should always start with the temperature. So at which the vapor pressure, temperature at which the vapor pressure equals, it can be external or atmospheric pressure, like that. That's how we define our boiling point. And then we've been asked 4.2, what is the relationship between the strength of intermolecular forces and the boiling point, right? So it means here, what is the relationship between the intermolecular forces and the boiling point, right? So it means if you are increasing your intermolecular forces, it means now the strength, or if you're increasing the strength of intermolecular forces, the boiling point is going to be higher. Okay, so the stronger the intermolecular force, can just say the stronger the intermolecular forces, I'll just write IMF there, and then the stronger the intermolecular force, the higher the boiling point, like that. Okay, so or else we can actually refer to as what you can actually refer it in terms of like the weakness, right? So it means the weaker the intermolecular forces, the lower the boiling point. So what we are saying here is that the boiling point is directly proportional to the strength of what is to the directly proportional to the strength of the what of the intermolecular forces. So if you increase the strength, if the strength of the intermolecular forces increases, then the boiling point also increases. If you decrease the strength of the intermolecular forces is actually less, the boiling point is also going to be what to be less there. Okay. Then 4.3 says which of the hydrogen halides A, B, C, or D in the table above has 4.3.1 highest vapor pressure, then refer to the boiling point in the table above to give a reason for the answer. Okay, so in terms of this one here, the one with the okay, the one with the lowest boiling point. Okay, let's just like look at this again. The one with the highest, so the first one here, highest boiling point is going to be this one, then followed by which one? There as well decreasing, so it means this is 2. Then after that, it means here negative 67. This is going to be 3. Then 85 is going to be 4, right? So here, they're saying which of the hydrogen halides there, A, B, C, or D, in the table above is the highest vapor pressure. Okay, so this is how it works, right? So I'm going to write my MP there, which is my melting point. I'm also going to write my BP there, which is my boiling point. Then versus I'm going to put a VP there. Okay, so what happens is that whenever the melting point and the boiling point are high, vapor pressure is going to be low, right? Okay, that's the relationship there. Then also if this vapor pressure is actually high, the boiling point and melting point are going to be less there, all right? So in this case, which highest, which of the highlights the A, B, or C, D in table above here, see has the highest vapor pressure. So in terms of the vapor pressure, it means if it's going to be having the highest vapor pressure, it must be having the lowest boiling point. So the one with the lowest boiling point there is going to be B, right? So your answer is B there, or you can write HCl there, HCl like that. Okay. So now we've been asked to give a reason for this, right? So the reason is that this has got the lowest boiling point, lowest boiling point. Okay, that's the lowest boiling point. Remember, vapor pressure is inversely proportional to both our melting point and boiling point, as I've already shown there at the top. Okay, so which one is the strongest intermolecular forces, right? So the one with the strongest intermolecular forces should be the one that is actually having the highest boiling point. In terms of this, the one that is having a highest boiling point there is going to be our option A there with a boiling point of 19,4. So it's going to be A or just our HF like that, or HF, right? Okay. Then we proceed to the next question that reads uh, on the graph paper provided, draw a line graph to represent the boiling points of the hydrogen halides. Then we've been asked to label the axes clearly and give the graph a heading, right? Okay, so now what we're going to start with is to give this graph our heading there, right? Okay, so here let me just like scroll to where my graph is. Okay, so here we're supposed to start with the heading of the graph, right? So we're going to say this refers to boiling points. Boiling points. What are we boiling there? Of 4 hydrogen halides, right? So we can just say of 4 hydrogen halides, or just like hydrogen halides, various different boiling points of different hydrogen halides. Hydrogen halides. Like that, okay? Then after that, now we're supposed to indicate or label our graph, right? For us to be able to label this graph, now we're supposed to look at it in terms of the scale, right? Okay? So in terms of this here, what you're going to have here is our okay, what are we having? We're having our hydrogen halides, then we're also having our boiling points. Okay, so let's label our x-axis and our y-axis there. Okay, so on the side here, we're going to have our boiling points, right? I'll just say BP and then in degrees Celsius, right? Boiling points in degrees Celsius. Then at the bottom there, I'm supposed to refer to the hydrogen halide since we're having difference of them, right? So I'm just going to say at the bottom there, we're having our hydrogen highlights. So this is hydrogen highlights like that. Okay, so now we're supposed to plot the values there. So now we're going to look at the lowest going to the highest, right? Okay, so now the lowest point there is negative 85. And then the highest temperature is going to be 19, right? So it's going to be 19 degrees. Okay, so if we are going to start there, I can say 20 going downwards, right? So I'm going to say 20. Let's say the highest temperature is going to be 20 there. Okay, then I use a scale of 20. If I'm using a scale of 20, so 0, it means here I'm going to have a negative 20, then negative 40, negative 80, negative 100 there. Okay, then going downwards again, I can actually put another one which can be a negative 120, but since already we are having the maximum value as a negative 85, I think the scale is actually fine like that. Okay, so now we need to label different temperatures there that have been given, right? So we're told the HF boils at what degree? 19,4, right? So we're going to have our HF at 19,4 there. So it means almost 20. So I'm going to go and label my 19,4. It's almost 20 there. Okay. Let me just like use this red so that it can be visible. Okay. So I'm going to start from there. It says 19,4, right? Okay, so 19,4, I can start from somewhere there, around somewhere there. Okay, let me just put my X there. Let's assume that's my 19,4. Then after that, I can go to the next one, which is my from 19,4, I'm having a value of negative 85, right? So it means from 19,4 to a negative 85, right? So it means it's gonna go down for negative 85 there, right? Okay, so 80, then it means along the what, since it's 20, so I can put it somewhere there, then my 85, let me just put it somewhere there. Then after that, now the next one is our HBr, which is a negative 67. So it means it increases a bit to negative 67. So negative 67. So it means here it's negative 20, 40, 60, okay, 80, 100. No, I need to change my scale there. 40, 20, 40. So here I will actually change this. So I'm going to say negative 20, negative 20, 40, it should be negative 60. Negative 60 there. Then I'm going to have my negative 468, then negative 100 like that. Okay, so the other one there, if we were to go up a bit, it was on negative 80, was it 84? Yes, negative 85. So negative 85. So we need to fix that one there. So it's going to be negative 85 there. So my negative 85, so 85, so it's 80, somewhere 85, somewhere there. Let me just like put it somewhere there, 85. Let me just say it was there. Okay, then after that, the next one, next of my values is what? Is negative 67. So it's a bit up there. So negative 67 is a little bit up there. So it's going to be 67. So 67. So it means here, somewhere there, I can put my 67 somewhere there, like that. Okay. Then the final one there, the one that we're actually going to have is going to be our D, which is negative 35.5, right? So it's a negative 35.5. So negative 35, 20, 30. So it means 30 is in between these two, right? Okay. So 30, 35, I'll go up a bit like that. Then after that, I'm supposed to join all these lines, right? So, okay. So it means I'm supposed to join there from there. I don't have a ruler, but I'll just like try. So we're supposed to join them like this. Then the next one there go up like that. Then the last one there like that. Okay. So this is supposed to look like this. Okay. So uh we started with our what? HF, then HCl, HF, then HCl. So it's going to be my HF there. HF. Then after that, what did I have there at the bottom? I'm going to have my HCl. So HCl. Then let me just like write this one at the top, my HF there, so that you can see that it aligns with this one. HF there. Then my HCl going downwards there. Then after that, the other one was what? The other one was HPR and HI, HPR and HI, HPR and HI. So if I can just like write there, let me try blue, maybe it's visible. HPR, HPR, and then the final one there is going to be my HI, like that. Okay, so that's how we're supposed to plot our graph there. Okay. Then we proceed to question 4,5. Then it says compare compounds A and B. Compare compounds A and B. Refer to the type and strength of the intermolecular forces. Okay, so we're supposed to compare A and B and refer to the type and strength of the intermolecular forces and energy needed to explain the differences in a boiling point. Okay, so in boiling point between hydrogen halides. Okay, so differences in boiling points like that. So I'll just say, okay, so let's start in general trend there from A. So in A there, hydrogen halides, right? So A, uh, HF, okay, that's my A there. My HF, okay, I have hydrogen bonds. HF has hydrogen bond, hydrogen bonds. Remember when I said uh, whenever, how do you identify your hydrogen bonds is when your hydrogen is bonded with fluorine, oxygen, or nitrogen. That's why we're saying this one has got what? Hydrogen bonds, right? Okay. While let's compare it with the other one. Okay, so let's look at the last one there. Compare A and B, A and B, A and B. So your B there. Let's then compare A and B to refer to the type of strength of intermolecular forces, right? Okay, so we're referring to B there. Okay, B. Okay, so after saying that, now we're going to say okay, our D there, our B there, which is our HCl there, our B there, which is our HCl. So HF has hydrogen bonds while HCl, while HCl has dipole forces, dipole forces like that. Okay. In terms of the strength of the intermolecular forces. Okay. So I'm going to say hydrogen bonds are stronger. Hydrogen bonds are stronger than dipole forces, dipole forces. Okay, so more energy is going to be needed. More energy is needed to overcome is needed to overcome intermolecular forces, intermolecular forces in hydrogen bonds. Specifically, here we're talking about HF. Then more energy is needed to overcome intermolecular forces in hydrogen bonds than in dipole forces, than in dipole forces, specifically in our HCl there, our HCl, like that. Okay, so this is how you're supposed to answer this question. Then after this, we are done, and that's a total of 50 marks. With that being said, thank you.